Welcome students. Today I will be discussing the lesson 9. The topic is GPS position. As you know, we make use of GPS to find out the location of any points or station, but we need to know in how this point is designated or how GPS represents this point, and in this class we will be discussing on that. Finally, we will make use of the location of the position of the point for making map. So, we need to know how that position that has been given by the GPS need to be converted or transformed to some coordinate which is useful for mapping purpose. So, this lesson will be discussed under these following heads, like first I will introduce to the topic, then how GPS provides the position, then we need to convert that position from one form to other. Now, to know more about this GPS position, we need to know some more fundamental things like different salient surfaces of the earth, different types of height, their transformation, then finally global to local conversion. As we know, as we have already learnt, that GPS is used to determine the position of any point, but that point GPS provides in a global reference system, and to understand the global reference system of GPS positioning, we need to know different types of surfaces and heights, and as we know that the engineering projects require local coordinate. So, we need to convert, if we want to make use of GPS observation for our engineering work, that has to be converted to local reference system. So, that conversion we will be learning in this class. Now, GPS provides position in a global reference system that is known as WGS84 system. WGS84 global reference system. The position of any point under this reference system may be two ways. One is that Cartesian, and as you know, Cartesian coordinates are defined by x, y, z, and it may be geodetic. So, it is latitude, longitude and height above reference surface. Now, in order to know really this, we need to define this axis. Now, to define axis, first we have to define the origin. Actually, in case of WGS84, the origin of the earth is taken as the center of the coordinate system, and the line which represents the axis of rotation of the earth as the z axis. Now, we know that the earth is rotating about some axis, and that is actually an imaginary line, and but on the surface of the earth that line intersects at some point, and we have constructed some station here in the northern hemisphere. It is the in the north pole, and another station in the south pole, and so line joining between these two is the z axis. Next, So that z axis is the most fundamental axis in our Cartesian coordinate system. Now if we imagine an infinite plane passing through this the primary meridian, which is the meridian passing through Greenwich, we will find a line like this and an infinite plane which is perpendicular to the z axis and passing through the center of mass of the earth, that is the equatorial plane. So if we take the intersection of the equatorial plane and the, if we take the, this is the equatorial plane, this is the plane which is this is the line of intersection of the surface of the earth with the equatorial plane, and if we take an infinite plane passing through the prime meridian, there will be an intersection like this with the surface of the earth. Now this intersection point, if we imagine a line through that point, that is our x axis. In this way we define the x axis, z axis is the primary axis. First we define the origin, then we define the z axis, and with reference to z axis, one infinite horizontal plane passing through the center of mass of the earth perpendicular to the z axis, that is the equatorial plane, and another plane, infinite plane passing through the z axis as well as through the center of mass and perpendicular to the equatorial plane and passing through the prime meridian, that is an intersection of that two line will be a point. Through this, if we pass this line, that is the x axis. Now if we imagine another line which is perpendicular to the x axis in the equatorial plane, then in the right hand direction, so that is the y axis. So in this way x, y, z axis is being defined for WGS84 coordinate system. So now if we imagine any point on the surface of the at any point, so that may be given by, if we drop a line perpendicular in this in parallel to z axis, and if we take a line parallel to y axis and a line parallel to x axis, this is the x coordinate of this point, this is the y coordinate of this point, and this is the z coordinate of this point, or x1, y1, z1. So x1, y1, z1. Now this is where how Cartesian coordinates is being defined, and we can get the position of any point. Another system in which the GPS position we get, that is the geodetic coordinate. For that, first we have to define a reference surface which is called reference ellipsoid. Reference ellipsoid, so in this figure you can see this is the reference ellipsoid because it is a sectional view, so it looks like this. Now an ellipsoid is an ellipse which rotates about the minor axis, and it is defined by the semi major axis and inverse reciprocal of flattening. So this is the two parameters how we do define the ellipsoid. Now in case of WGS84, it is the semi major axis is given by 6, 3, 7, 8, 1, 3, 7 meter. So you can say 6,378.137 kilometer, or and the reciprocal is 298.2572 like that, 2572 like that. Now this is the reference surface or reference ellipsoid above which the height is measured in case of WGS84 coordinate system. Now suppose this is the same point, if we take, that will be defined by a latitude, longitude and height. Now for the height, latitude means, now it is, if we drop a actually this is the reference surface, suppose this is the reference surface. So if we drop a normal on it, it will reach to the equatorial plane at some point like this. Now if we draw like this, so from this equatorial plane the angle above this, that is the latitude, and this is the reference meridian, that means this one, is the longitude of the place or point, and since this is the reference surface, reference ellipsoid, this is the height, and this is called also geodetic height, height above reference ellipsoid. So for the same point P, we can, GPS provides us position in two ways. One is that Cartesian coordinates x1, y1, z1, another is that latitude, longitude and height. So this is the most fundamental way how the GPS provides us the position of any point, and this is with respect to a global reference system. Now many times we need to convert between the geodetic coordinate and Cartesian coordinate. So if we know the geodetic coordinate phi, lambda and small h, then the Cartesian coordinate can be determined by using this relation, where r is given by this. R means it is the distance from the reference ellipsoid to the point where this, if we extend this z axis, it will cut at some point. So now this is the radius of curvature at this point, this is called r. R is the radius of curvature at the point on the reference ellipsoid at which the normal from the point is intersecting. So and the r can be determined by using the semi-major axis as well as semi-minor axis. B is the semi-minor axis. So and also it depends on the latitude of the place. So the radius of curvature at any point on the surface of an ellipsoid depends on three factors: semi-major axis, semi-minor axis as well as latitude of the place. So and it is given by the relation a square divided by a square cos square phi plus b square sin square phi to the power half. So using this relation we can convert the geodetic coordinate to Cartesian coordinate, and inverse, by inversing we can get the Cartesian coordinate, from Cartesian coordinate we can get also the geodetic coordinate. To understand the GPS positioning better, we need to know some fundamental things like the surfaces of the earth. Actually fundamentally it is the surface of the earth means the place or the surface on which we people are living, that is the actual surface of the earth, actual surface of the earth. But it is, this surface is very undulating and you can see that any point may change any time, because we are going for cutting, filling, and we are doing so many activities on it. So it is very difficult to know or model this type of surface. Now as we know that the earth is a bit ellipsoid in shape, so geometrically earth is mathematically or geometrically earth is defined as ellipsoid surface. Earth is defined as a ellipsoid surface mathematically, but or geometrically, but it really does not represent the earth or define activities that we define, engineering projects that we do carry on, we will not be able to do by considering the ellipsoid surface of the earth as the reference surface. So we need to have another surface which is called geoid surface, or which is called physical surface of the earth. Physical surface of the earth. Actually this is a surface which represents an equipotential. It is an equipotential surface. That means if we consider one point here, another point this, then there will not be any energy required to go from this point to that point, because these points are on equipotential surface, and most of the engineering activity depends upon the gravity energy and all these things. So we represent the earth through this surface, and this is called physical surface of the earth. And to make it a reference, actually if we consider the earth something like this, we may get infinite numbers of equipotential surfaces around the earth. This is the earth, we can get infinite numbers of surfaces around the earth. So but which one we will consider as a reference? So scientists have considered that equipotential surface of the earth will be considered as reference, which best approximates the mean sea level of the earth, because as we know that the earth's surface is mostly covered by water, 70% of the surface of the earth is water. So the equipotential surface that best approximates the mean sea level of the earth is considered as the reference surface, and that is known as geoid. So geoid is considered as the reference physical surface, and this actual surface of the earth is whatever is available, and the ellipsoid surface, this is a variable because it will depend upon the value of A and 1 by f. So depending upon our requirement, we can vary the value of A and f, and we can take this different ellipsoid surface. And for WGS 84 ellipsoid, already I had shown you that the value is taken as A and f, and with that value of A and f, the WGS 84 has been decided. Now if we say a point, suppose again P, whose coordinate is xp, yp and zp, or is phi p, and this is, now this point P may have different types of height depending upon from which reference we are considering. Now if we consider the height of this point above the physical surface of the earth, then this height is called as orthometric height. So h is the height, orthometric height. And if we consider the height of this point with respect to ellipsoid, then it is called geodetic height. Now orthometric height is with respect to geoid, and now this geoid is constant for the earth, but geodetic height is with respect to ellipsoid. Now as I told you, this ellipsoid may vary from your consideration on different project to different project or different system. So this ellipsoid height may vary from place to place. For the same point, if we take different ellipsoid, we can have the different ellipsoid and different height, geodetic height. But in case of GPS, we take the ellipsoid, the WGS 84 ellipsoid. So in case of GPS, this height is with respect to WGS 84. So we should write WGS 84. That means we are taking the WGS 84 ellipsoid as the reference surface. This is the orthometric height. Now one more point. Now from GPS observation, we will be getting this value. Now how to get the orthometric height? So now you can see from here, if we know this separation, then if we add this with, if we subtract this value from this, then we will be able to get this. And this separation, which is the separation between geoid and ellipsoid, that is called geoid height or geoid undulation, and represented by n, geoid undulation. Now in this case, if we this h WGS 84, we can get it from GPS observation, and if we know what is the value of n, which is the geoid undulation, we will be able to get h equal to h minus n. Now in some cases, in many cases, this surface may be below this, or in some cases it may be above this. So generally we write it like this. So by knowing the geoid undulation and from GPS observation, we will be able to find out the height, orthometric height, and this is the height which we need for our engineering projects. So this is what it is written here in this slide: ellipsoidal height, geoid height, orthometric height. Now this is the figure what I have shown you. So depending on the position of the geoid and ellipsoid surface, the relation between orthometric height and geoid height, it can be given by h plus minus n, small h plus minus n equal to capital H. Now the problem is how to get this. Now in case of GPS observation, we know we will be able to get this value, and we know this reference is the WGS 84 ellipsoid, WGS 84 ellipsoid, and WGS 84 coordinate, WGS 84 reference system also provides us a mathematical model which represents the geoid, that is called Earth's Gravitational Model 2008. So it is denoted by EGM08. This is a mathematical model which represents the geoid surface of the earth, and it is available in the internet. So by making use of this, we can directly compute the if we provide the latitude and longitude of a place, then we will get the value of n at that place. So this is one of the ways. If we go to this link and a software will come, in that software you have to give the latitude and longitude of the place, and that software will provide you the geoid undulation with respect to WGS84 ellipsoid. You have to keep it in mind, and once you know this value, automatically from GPS you know this thing, so you will be able to calculate orthometric height. Further, as I told you that engineering projects makes use of local coordinates for its all activities. So, and on the other hand, GPS provides us global coordinates either in Cartesian coordinates or in geodetic coordinates. So, to make GPS observation useful for our engineering works or mapping purpose, we need to convert the global coordinates to local coordinate, and generally the local coordinates we do represent by a system called north, east and orthometric height or vertical height. Vertical height also can be told as orthometric height. So we need to convert our Cartesian coordinate or geodetic coordinate to northeast and height. Now for this, if you want to do this thing, we need to have few more things. Suppose I want to find out the local coordinate of any point Q. So suppose the local coordinate is represented by NQ, northeast and height of the point Q. This is the local coordinate. I can represent it by the matrix called this. In order to know the local coordinate of the point Q, we need to know the local coordinate of the point P. That means we need to know NP, EP, HP. That means this is the control point. That means a point. So a point P will be behaving as a control point. Control point means a point whose position is known and its position in terms of local coordinates should be known. Apart from that, we have to take observation at P, point P, and we will have the Cartesian coordinate using GPS like this, as well as we need to see the local coordinates. We need to take the GPS observation at station Q, XQ, YQ, ZQ. So this is known from GPS observation, this is known from GPS observation, and this is should be available. It should be available before. So by now using this we can go for, now del x means this is the change in coordinate, means xq minus xp, like that, del y, del z. These are the three things we can determine by using this and this. After having this thing, by using this relation LQ, we can get LP plus a matrix del x, del y, del z. This matrix is based like this, minus of sine, cosine of, like this. So by multiplying this matrix with this matrix, we will get some value which has to be added with this, then we can get the local coordinate of the point Q. In this way we can go for conversion from global Cartesian coordinate from GPS observation to local northeast and height coordinate to be useful for all engineering works. With this I like to complete today's lesson, but before that let me summarize. GPS provides position in global reference system, either or both we can get Cartesian coordinates xyz or geodetic coordinates lambda phi h, latitude, longitude and height. There are three types of surfaces which we consider for geodetic study purpose or GPS positioning purpose. The actual surface of the earth where all the activities are going on, the ellipsoid surface which is the geometrical surface which we do for our mathematical work, and the physical surface of the earth, that is an equipotential surface, and geoid as the reference which is really reference surface for all our engineering works. And for all our engineering works actually we need to have the local coordinates in terms of north, east and orthometric height, which we can get from GPS coordinate through conversion. With this I like to conclude, and next class I will be talking on GPS principles and observables. Thank you.